So welcome to my channel. Now we will solve some previous year questions, obviously memory based question, because BARC does not replace its official question paper. Okay, so let's start. So first question is given as find the eigenvalues of this matrix. Okay, matrix. Let's take this matrix is as A. So what will be the trace of A? Trace is addition of diagonal elements, so it will be 2 minus 5 plus 3 0. And what will be the determinant of this matrix? So determinant, if we calculate the determinant about this row, then it will be 3 times minus 10 then plus 6, so it is minus 12. So let's find the answer. So if we choose this option, minus 1 1 3 does not give me minus 12, but option C gives minus 12 here. Minus 4 1 3 is minus 12, and if we multiply them, that is the determinant. If we add them, it gives 0, so it satisfies this two expression. So that's why option C will be the correct one. Second is find the derivative of x to the power x. Okay, so it is in form of u dot v. So let's take x take as it is. Derivative of 2 to the power x gives us 2 to the power x as it is, and ln 2. Okay, then plus 2 to the power x is taken as it is, and derivative of x is 1, so it will be 2 to the power x into 1 plus x ln 2. So option C will be the correct one. Now next question. On heating a diamagnetic substance, its susceptibility will be. Basically, for diamagnetic substance, it has zero magnetic moment, and therefore there are no permanent dipoles. Okay, there are no permanent magnetic dipoles. That's why if we increase temperature or if we decrease temperature, it does not affect on the magnetization of that material. Okay, now susceptibility is basically ratio of magnetization divided by applied field, magnetic field. So that's why here there is no change in the susceptibility during the heating of this type of magnetic substance, so it will remain same. Now we talking about uh, paramagnetic substance. For paramagnetic substance, the xi varies with 1 by t. Okay, so with increasing temperature susceptibility will be decreased, and for with decreasing temperature susceptibility will increase. Okay, next one. 1 mole of ideal gas undergoes a reversible isothermal expansion at temperature T from V to 2V. Okay, now we have to find the change in entropy. Okay, so N is 1 mole. Okay, temperature is fixed, constant temperature, and initial final volume is V, initial volume is 2V. So let's since it is an isothermal process, reversible isothermal process, so what will be the work done for this type of process? So work done will be inerty ln V final divided by V initial. So what will be the expression of work done? Now n is 1 here, so RT ln in final volume is 2V and initial volume is V, so it will be only 2, so RT ln 2. So this is the work done. Now according to first thermodynamics law, we know that is dq equals to du plus pdv. So pdv is nothing but work done. Now for this process, that is for reversible isothermal expansion, du is 0, so therefore dq is pdv, that is the work done, pdv, that is RT ln 2. Okay, now change in entropy, that is the ds, is nothing but dq by t. Okay, change in entropy is nothing but dq by t. So what will be the dq by t? That is RlN2. Okay, so answer will be option A. Next, so find the current through the load resistance RL. So what will be the current through RL? Now to find the current through RL, this is the IL load current and this is the IZ general current. But to find current through RL, we need to know the value of RL na. Okay, but RL is not given here, so this one is incomplete one. Okay, so in SU group, that is SUN group, the number of bosons will be, so SU stands for special unitary symmetry group. Okay, so it is in standard model. So what will be the number of bosons? So in general, if we are talking about SU2, so here n indicates the degree of that symmetry group. Okay, so for SU2 it indicates, or it uses for uh, weak interactions. Like for weak interaction bosons, there are three bosons, that is W plus, W minus and Z. So it obeys like 2 to the power 2 minus 1. Similarly for SU3, this symmetry group used for uh, strong interaction, and uh, there are 8 strong bosons here. So it follows also 3 squared minus 1, like that. So in general we can write the number of bosons is basically n squared minus 1. Okay, that is n squared minus 1. So option C is the correct one. Next, for 1D potential given as v of x is this one, half omega square x square for x positive and x for infinity for x negative. Okay, now wave function is given 1 by root 5 psi 0 phi 0 plus 2 by root 5 phi 1. Okay, so phi 0 and phi 1 are the ground state and the fast expected wave function correspondingly. The expectation value of the energy, so we have to find the expectation value of the energy. Now from the question we can say that the potential that is given here for x positive, it follows this x squared law of potential, that it is half harmonic oscillator. Okay, like this. So for half harmonic oscillator, the energy value is given as n plus 3 by 2, so it is 1D, so it will be 1 by 2 n plus 1 by 2 h cross omega for odd n equals to 1, 3, 5 and so on. So for phi naught is wave function corresponding to the ground state. So ground state will be corresponding n equals to 1 case. For n equals to 1, it gives 3 by 2 h cross omega. This is corresponding phi 0, and for the first excited state n will be 3, so phi E3 will be, it will be 7 by 2 h cross omega. So this is the energy corresponding to the phi 1 state. So what will be the expectation value of the energy corresponding this psi state? That will be expectation of E is basically given as mod of Ci square, that is the coefficient of these states phi naught and phi 1, into the energy eigenvalue corresponding these two states, that is Ei. Okay, so for the first state, mod of 5 whole squared, so it gives 1 by 5. Corresponding energy is E1, that is 3 by 2 h cross omega. Okay, then plus mod of 2 by root 5 mod square, it gives 4 by 5, 7 by 2 h cross omega. Okay, so as a whole it gives, I think 1 by 10 is common out, so 3 plus 4 is 7, so 7 by 3 plus 28, 3 plus 28, it gives 31 h cross omega by 10, 31 h cross omega by 10. Okay, so option A is the correct one. Next, so in 1D potential box, the number density, what will be the number density? Okay, so variation of number density with the energy. Okay, so for 1D potential box, we know the energy E basically n square pi square h cross square divided by twice m l squared. Okay, if we consider the length of the 1D box is L. Okay, so from here we can find out n squared. So n squared is directly proportional to E, therefore n will be proportional to root under E. Okay, now here we have to find out the number density, that is the number of so n, here n indicates the states na, so n is the corresponding the state. For ground state n will be 1, for first state n will be 2, so here n will be the state, indicates the state. So number density, that means per unit energy interval what will be the number of states, that is dn by E. So dn by E will be the number of state. So if we differentiate this root under E with respect to E, it gives basically 1 divided by root over E. Okay, so the number density is directly proportional with 1 by root under E. B is the correct one. Next, the probability of Sz for the down state, that means spin is minus h cross by 2, for the given state root under 3 by 5 and iota root under 2 by 5. Okay, so let's solve it. Now for the Sz equals to minus h cross by 2, the state will be, the eigenstate will be 0 1. Okay, this is the state. Now we have to find out the probability for this state, so let's take it as phi and it is psi, get psi, this is get phi. Okay, so probability will be psi phi mod square. Okay, this is the probability. So bra psi will be 0 1 and ket psi is basically root under 3 by 5, then iota root under 2 by 5 mod square. Okay, so it gives only iota root under 5 mod square, so mod square is gives us 2 by 5 only, so the probability will be 2 by 5. Okay, next this is the equation given as singularity is 1 and minus 1, so nature of the singularity, so obviously x equals to 1 minus x square equals to 0, so x will be plus minus 1, and here plus minus 1 are the regular singular point. Okay, singularity is there at plus minus 1 and the nature of the singularity is regular singular point. Okay, So next, question number 11. So an harmonic oscillator, okay, and it is anisotropic. So v of x given as this way. So if we rewrite this v of xyz like this, that is half m 2 omega then squared, then x squared, plus half m 4 omega whole squared, then y squared, plus half m 6 omega whole squared z squared. Okay, so the ground state energy. So simple. For in case of anisotropic harmonic oscillator, energy is given as nx, ny, nz is given as nx plus half h cross omega x plus ny plus half h cross omega y plus nz plus half h cross omega z. Okay, so obviously here omega x is 2 omega, omega y is 4 omega, and omega z is 6 omega. So what will be the ground state energy? For the ground state energy, nx, ny, nz will be 0 0 0. So for 0 0 case, it gives half into h cross into 2 omega plus half into h cross 4 omega plus half into h cross into 8 omega, sorry 6 omega. Okay, so here h cross omega plus 2h cross omega plus 3h cross omega, so as a whole we get 6h cross omega. Okay, so option B is the correct one. So next, the ratio of the rotational energy for the state 4 plus and 6 plus. Okay, so for question number 12, we know that the rotational energy is proportional to j into j plus 1. Okay, so if we find out the ratio for these two states, very simple. J, let's take it as E4 and E6. It gives 4 into 4 plus 1 divided by 6 into 6 plus 1. So is 2, 2 by 3, then 2 times 5 is 10, and 3 times 3 times 7 is 21. So 10 by 21. Okay, ratio of the rotational energy for these two states. Okay, 10 by 21. Next is the ratio of the second nearest neighbor to the first nearest neighbor in FCC. Okay, so for FCC structure, the first nearest neighbor distance, first nearest neighbor distance is basically uh, diagonal is root 2a. Okay, then divided by 2. So a by root 2 is the first nearest neighbor distance, and the second nearest neighbor distance is basically second nearest neighbor atoms are placed at the corner. Okay, so second nearest neighbor distance will be a. So if we want to find the ratio of second nearest neighbor to the first nearest neighbor, so for second divided by first case, then it gives a divided by a by root 2, so it will be only root 2. Okay, so the answer will be root 2. Okay, next question is allowed transition for the gamma ray. Okay, so for gamma decay, what will be the allowed transition? uh, J initial is given and also J final is given. Okay, so here J initial is 7 by 2, pi is the parity, here is even parity, plus sign is there, and J final pi is 3 by 2. It is also even parity. So we have to check what will be the change in del L value. Since it is gamma decay, so obviously del S will be 0. So del J is nothing but del L plus del S. So del L is del J. So what will be the del J value? We have to take the mod value now. So for the final state and the initial state. So it will be mod of 7 by 2 minus 3 by 2. So it gives 4 by 2, it is 2. So del L value is 2. Okay. Now for the gamma transition, the selection rules are, so if the change in L value is L, okay, if the change in L value is L and if the L value is odd, okay, so if the change in L value is L and if L gives odd value, then for change in parity case, if change in parity yes, then it indicates the electric pole, I think. Okay, for L it will be 2 to the power L pole, it gives electric pole. Okay, electric pole. And if L for case of L odd, if parity change is no change in parity, then it indicates magnetic pole and it will be magnetic 2 to the power L pole. Okay, so using this, similarly for L even case, if the change in L value is even, then parity change yes means it will be magnetic pole and parity change no means it will be the electric pole. Okay, now let's find for this case. So here del L value is 2. Okay, so del L value is 2 means it is even value. Okay, so for even value we have to check the parity. So parity is positive for the initial state and parity is also positive for the final state. So there is no change in parity. Okay, so no change in parity, no. So for even case and no change in parity, obviously it indicates the uh, electric pole. Okay, electric pole. So here del L is 2 here, that means it indicates the electric pole, it indicates E2 case. Okay, E2 and corresponding to uh, M3 I think. Okay, so del L is 2 here, so del L is 2, that means for no change in parity, that is E2. Okay, that is E2, no change in parity, it gives E2 only. And if change in parity, then it gives M2, no change in parity, so E2 only. So the most intense radiations are E2 and M1 I think. Basically we have to consider 7 by 2 plus 3 by 2, so it gives 7 by 2 plus 3 by 2 10, so 5, so we have to consider 2 3 5. Okay, so for 2 it gives no change in parity, so for 2 it gives E2, and for 3, okay, for 3 it is odd, no change in parity, so it gives magnetic pole, that is M3. So answer will be E2 and M3. Okay, E2 and M3. Let's so here Ji and Jf given. So what will be the del J? Del J is basically del L. Now del L basically here del J, that will be mod of 7 by 2 plus minus 3 by 2 to mod of 7 by 2 plus 3 by 2. That means we get three values from here. That is, from the first one it will be 2, and for last one it will be 5. So total values are I think 4. So 2, then 3, then 4. Okay, 2 3 4. So for 2 case, no change in parity, it gives the electric pole. For 3 case, no change in parity, it gives M3 magnetic pole. For 4, again even number, no change in parity, it gives electric pole E4. And for 5, no change in parity, it gives M5. So answer will be B na, E2 and M3, E2 and M3, M3 and E4. Okay, option C is also correct, M3 and E4. Okay.